All right, welcome back. So in this lesson, we'll be looking at another method of solving first order differential equations. And it will be the case where we will deal with exact equations. And there's a special section in the textbook where they talk about different integrating factors for exact differential equations. But for the most part, I'm going to give you an overview of what an exact differential equation is and how to solve it. Before I get into this, you'll need a little bit of background on Calc 3 material. I would say just looking at, I guess, partial derivatives and looking how to find a potential function for what's called a conservative vector field. The methodology behind figuring out a potential function, it will be similar to solving for a general solution for an exact differential equation, right? So hopefully you have this knowledge, but if not, that's okay. I'm going to give you the specific techniques on figuring out a general solution for an exact differential equation. So with all that out of the way, let's get started. So the theory behind an exact differential equation. So it looks like this. So we'll have, when we actually write this, I'll erase this piece. So an exact differential equation, it has a formulation. It looks like this. Okay. dy equals 0. This is the formulation of an exact differential equation, right? Right, looks like this. Okay, and the theory on how this equation came about is we're going to look at a concept in Calc 3, and it's looking at level curves of multi-value functions. So a level curve looks something like this, right? So it's an equation where psi is a function in x and y, okay? And c is just an arbitrary constant, right? It's just an arbitrary constant, all right? So really, you are looking at what are my x and y values, what the x and y values will be if psi of xy equals to c. So for example, if I have uh, uh, this type of level curve, right? C is just any constant, right? Would you know what these level curves would describe? Well, we would have to see um what uh uh what would be our values for C, right? So which C values would be valid and which ones are not, right? So um so in other words, uh yeah, so if we can say if C is 0, well, we'll just have uh lines y equals plus or minus x. So let me just draw in a graph here. So the level curves, right? So C equals 0 will have just lines at y equals to x and then y equals to negative x, right? If C is 1, right, we'll get this equation. Do you know what this describes? Well, if you said it's a hyperbola, you are right. This describes a hyperbola. Okay. So if C is 1, we're going to have a hyperbola like this. Right? So this would be the level curve if C is 1, right? So we're going to have a hyperbola opening with respect to the horizontal. Okay. So they called it the transversal axis, right? So the transversal axis for a hyperbola is um, the x-axis. Okay. And then if we just continue adding on different constant values for C, we will get just hyperbolas opening with respect to the x-axis, right? So we're going to have another hyperbola. So just a much bigger hyperbola right here. This is where C is 4. And then if I were to look at different negative values for x, so if I were to look at different negative values, right, -1, well, that would be y squared minus x squared equals 1. This is just another hyperbola. And so the hyperbolas this time would open this way, right? If it's negative, the hyperbolas would be opening up and down. Okay, so the level curves would be just a family of hyperbolas, right? And how they open just depends on the C value, right? So this is just another hyperbola. So the level curves for this example would be a family of hyperbolas. Okay. So that's just a basic knowledge on Calc 3 for you. So I'm going to erase this here. And I'm going to go over how the exact differential equation is formulated. So that's right there. All right, this example. And right there. It's constant. All right. So now y, this would be a function in the independent variable, right? So this is a function in x, right? The independent variable. And so if I were to differentiate both sides of this equation with respect to x of psi, right? This will be 0. The derivative of a constant is 0. Well, we're going to have to use the chain rule for this equation here, right? And then psi is a function of x and y. So what that means is we're going to have to take the partial of psi with respect to x first times dx, which in this case it's 1, right? Plus the partial of psi with respect to y times dy dx. Okay, and this equals to 0. And we can actually solve for dy dx. So I'm going to write dy dx as this shorthand. So it'd be minus psi with their sub x and then psi sub y. Right, this is the partial of psi with respect to x here, and this is the partial of psi with respect to y there. Okay, so yeah, so that would be dy dx, right? And then this is just, you know, this equation right here, this is how we would express any differential equation, right? So we can express any differential equation like this, or actually, yeah, like this, right? We'll have some function psi of x and y equal to c, okay? And then, and this is just one method of solving the dy dx term, right? Just use implicit differentiation and then integrate with respect to x, and there would be your general solution, right? So for exact differential equations, your solution will look like this form, right? But so if I were to say that psi of x equals to m of xy, and then psi with respect to y equal to another function n, this is where the formulation comes from, right? So we'll have m plus n dy dx equals to 0. Or you can say m times dx plus n times dy equals to 0. Right? We could split off this dx term, right, by just multiplying that quantity to both sides, right? And then we'll get up to getting to this equation right here, right? Okay. And then another fact here is that psi has to be continuous. It has to be a continuous function. And their derivatives, psi x and psi y, they have to exist as well, right? They have to exist as well. So that's the important key here. So there's a test to show if a differential equation of this form is indeed what's called exact. And it uses this theorem in Calc 3 called the Clairaut theorem. Clairaut theorem. And essentially what this means is the mixed second partial derivatives of psi of x and y are equal. They have to equal, essentially. That's Clairaut's theorem. Mixed partial derivatives are the same. Okay. It doesn't apply for, not only applies for two variable functions, but also for more than two variable functions as well, right? So, and it also applies to second, third, fourth, fifth, how many number of derivatives of a function you want to take. So, yeah, mixed partial derivatives are equal. So that's going to be important. Not only that, shows that partial derivatives exist, but you have a continuous function as well. So you have a continuous general solution, right? So what that means is if we know that psi of x is m, and we know that psi of y is n, so what that means is if I take the derivative of this function with respect to y, right? If I take the derivative with respect to y here, so I'll have the second partial of psi with respect to x and then with respect to y, but that has to equal to the partial of m with respect to y. And then likewise, if I were to differentiate this function with respect to x, that would mean that the partial of psi with respect to x, and then you take that derivative with respect to x again. This is the same as taking the partial of n with respect to x. Now, by Clairaut's theorem, right, the mixed partial derivatives, the mixed second partial derivatives are the same. So that means the test to show a first order differential equation is exact is if the partial of m with respect to y has to equal to the partial of n with respect to x. Okay. This is the test of showing what is called an exact differential equation. Okay. If this is not, if this quantity is not true, then it's not exact. Okay. So that's the theory behind exact equations, and I'm going to highlight the process in solving an exact differential equation. Okay, so if we have an exact equation, m dx plus n dy equals to 0, if we know that's an exact differential equation, then we can say that the partial of f, capital F, with respect to x is equal to n. So what that means is, so we said before that psi of x is m and psi of y was n. They said f here, but it's the same idea. So we know that psi of x is m and then psi of y is n. Okay. So what you're going to do now is you're going to take this quantity and you're going to integrate with respect to x on both sides. So that is what this statement is saying here. Okay, so we want to integrate the last equation here with respect to x, and we'll get a general solution that looks like this form, right? So we're integrating with respect to x, but if you integrate a function, you have to incorporate a constant of some kind. Now, we're dealing with a function of two variables. So what that means is your constant will be a function of the other variable. So in this case, since we're integrating this equation with respect to x, the general solution will have a constant that is a function with respect to y. So, so do not forget that step. You'll have a not only a constant, but it's also a function with respect to the other variable. Okay, so I'll go over this in detail with some examples. Okay, but and then from here, from this point forward, you are going to determine what the g of y function is, right? So you want to take the partial derivative with respect to y, since we have a function in y as a constant. Okay, and then we want to substitute n for the general solution. Okay, and then from here he's going to solve for g prime of y. Okay, and then you integrate again, but this time it's respect to y. And it's going to be a function up to a constant, a number, right? A number, so not a function this time, it's going to be a number. And if you substitute the g of y into the equation here, you'll get a general solution that looks like this. Okay, capital F of x and then y of x. I should say that. Y is a function of x here. Okay, equals to c. You can do this whole process by integrating n with respect to y, and you'll have a function in x here instead of just y now. Then you have to take the derivative with respect to x and then integrate that function back with respect to x. And then you can derive a general solution from there, right? So those are just the steps, but it's probably best if I give out some examples and how we would solve a different an exact differential equation. Okay, so let's go over this one first. In order to solve a exact differential equation, we need to determine if it is exact, right? So determine if So I wrote out cosine of x, cosine y plus 2x dx minus sine x sine y plus 2y. Oh, shoot, 2y dy is 0, is exact. If so, okay, relatively straightforward, right? So we have cosine x cosine y plus 2x dx minus sine x times sine y plus 2y dy equals 0. We have to show that this equation is exact. If it is so, then we're going to find the general solution. Okay, so we want to label out what the psi x is. Okay, so so that will be m, but the m in this case is this function. So it'd be cosine x cosine y plus 2x, right? And we have the psi y quantity, which is labeled as n. And this right here is the psi, that is the n quantity. So the negative sine x sine y plus 2y, right? Okay. So, okay. So we have to take the derivative of m with respect to x, the derivative of m with respect to x. So that would be, so cosine of y is any term with y variables in it are constants. Okay. So the partial of m with respect to x is, so minus sine x cosine y. Oh, I'm sorry. With respect to y, excuse me. Okay, hold on a second. I gotta erase this. Doing all wrong. So to take the partial of m with respect to y. Shoot. All right, let me do that again. So, all right. So the partial of m with respect to y. So that would be minus sine y. X's are constant, so it would be cosine x plus 2x, so that's 0. And then a partial of n with respect to x, that would be minus cosine x sine y. And then plus 0. Okay. And it turns out these are equal. It turns out partial of m with respect to y is equal to the partial of n with respect to x. So it is exact. Bingo. Right. So it's exact. So now we can say that a general solution exists. So psi of x and y is the general solution, right? Such that the psi with respect to x is m, and psi with respect to y is n. Okay, so we now have psi with respect to x equals to, let me write out what m is. So cosine x times cosine y plus 2x. So now to get up to the general solution, what we need to do is we need to integrate both sides. right? So, 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 let me see what room I got. Oops. Okay. Let me see what room I got. All right, so psi of xy. Okay, so this would equal to, so we need to integrate this with respect to x. So this would equal to the integral of cosine x, cosine y plus 2x dx. And so psi is equal to, so it would be sine x cosine y plus x squared plus a constant, but this time your constant is a function in y, right? It's a function in y. So next step is solving for this h of y quantity here, right? So next, we're going to have to differentiate this quantity with respect to y. So that means psi with respect to y is equal to minus sine x times sine y plus x squared. That would be 0. And then we'll have a plus h prime of y. H prime of y. Okay, so we also know that psi of y equals to negative sine of x plus times sine y plus 2y. So that means negative sine x times sine y plus 2y equals negative sine x sine y plus h prime of y. Okay. These quantities are the same, so they will be 0. And so what you have left over is that 2y equals to h prime of y, right? Okay. And then if we just figure out what h of y is, it's just the antiderivative of 2y, right? So h of y is equal to y squared plus a constant, right? But essentially this constant will be on the right-hand side. And so the general solution, psi of x and y, this would be, so we'll have, where is it? Okay, so sine x cosine y plus x squared plus y squared, and that equals to c. All right. So that's the general solution. All right. So hopefully that made sense. Okay. How about this one? I want to think about where to write this other example. Well, this over here should be good. How about this one? Cosine theta dr minus r sine theta minus e to the theta d theta is 0. Try and see if that is exact. And if it is, try to find a general solution. If not, show work that it's not. All right. Pause the video and think about this. Okay. So I assume you worked on this example here. Now, if you notice, so we have r and theta, but that's okay, right? So this is the m function, then this quantity right here, that's n, we'll see, including the negative sign, right? So m, this is so let me write out. Let me write out f with respect to r. So it's cosine theta, and then f with respect to theta is equal to minus r sine theta plus e to the theta, right? So, so a general solution should satisfy these equations here, right? So, so if this is m and this is n, right? The partial of m with respect to theta is equal to negative sine theta, right? And then the partial of m with respect to r, I'm sorry, n with respect to r, this will be minus r cosine theta plus 0, and these are not equal, right? So this equation is not exact. So we have to figure out some other way to solve this. Let's see. Um yeah, you'll have to do some other method. But yeah, okay. Yeah, you'll have to do some other method. I don't think it's separate. I don't think it's separable either. So, okay, yeah, so that's an example of an equation that's not exact, right? So, um, let's see, what do I have here? I want to go over one more example. Uh, where there, yeah, so, um, so we'll deal with actually, I want to go over that one just in a second, but um yeah, I want to go over this example here too. How can I add in a new slide? Okay, so I'm going to stop here. I'm going to do another example. Yeah, so I'm going to do another example here. So, okay. Yeah, so another example. Um, is this one. So suppose we have this initial value problem, right? So we have ty plus te to the ty, t times y. Dt plus plus 2 dy equals 0. And we have that y of 0 is -1. Okay. So try to solve this initial value problem. Okay. Yeah, try pause the video and yeah, try to figure out this differential equation. Okay. So I assumed you worked this out. Okay. So first of all, So the methods we've seen in differential equations is separation of variables and then linear differential equations and then exact differential equations, right? So yeah, so as you can see, um yes, I believe it is separable. Okay. Yeah, I believe it is yeah, it could be separable. All right. But it's also an exact differential equation, right? So if I label this as M, if I label this as N, right? So M is e to the t times y plus t times e to the t times y. N is t times e to the t plus 2. Okay. So what that means is partial of M with respect to y, that would equal to e to the t plus t times e to the t. Partial of n with respect to x, we're going to have to use the product rule here. So we'll have e to the t times derivative t is 1 plus t times derivative e to the t, which is e to the t, and then plus 0. And it turns out they are the same, right? So this differential equation is exact, okay? So we have that so we have a function. So there exists a function, a general solution f, which the partial of capital F with respect to x is m, and the partial of capital F with respect to y is n, right? So so we know that x is equal to e to the t, or I should say t, the independent variable is t now. So let me rewrite this a little bit more clear. Um, so so there exists a function f of t y where f of t is equal to e to the t times y plus t times e to the t times y, and then f of ty, partial capital F with respect to y, t times e to the t plus 2, right? And so if we start off with this equation, if we integrate both sides with respect to t, right, f of ty, well, that equals to the integral of e to the t times y plus t times e to the t times y dt plus h of y, right? And so t times e to the t, you're going to use integration by parts. So we'll have y times e to the t plus y times, so it's t times e to the t minus e to the t plus h of y. The y times e to the t terms cancel. So you'll have your function equal to y times t e to the t plus h of y, right? Then if we differentiate this equation with respect to y, we'll have f of y equals to t times e to the t plus h prime of y. Capital F prime of y equals to this quantity, So that means t times e to the t plus 2 equals to t times e to the t plus h prime of y. So that means h prime of y is 2. So h of y equals to 2y plus a constant, right? And so f of t and y, this would equal to y times t times e to the t plus 2y. And that has to equal to another constant, c, right? So that's your general solution. Now the particular solution, um, now the particular solution, right, this is where if t is 0, y is -1. So the initial condition, 0 minus 1. So we'll have a -1. Oh, I'm sorry. So yeah. Okay. So t is 0. So that's 0. So we'll have a -2. So c is -2. And so f of ty, this would equal to um, y times t times e to the t plus 2y equals to -2. This is the particular solution. All right. Okay. Yeah, and if you solve for y, you can get this explicitly. So I'm just trying to make sure. So this equals to c over t times. And so that's 0, c over 2, so c is -2. Okay, yeah, great. So this right here is the particular solution, right? So there's going to be problems where you'll deal with special integrating factors. Um, but really, it's just using the same um, uh, technique as solving for exact differential equations. So you'll have what are called special integrating factors. And so if we have an equation like this, right? So if we are dealing with an equation that is not exact, but if we have sort of an equation that looks like this with mu, which is multiplied by a function mu of x and y, and that results in an exact equation, right? Then we call mu of x, y as an integrating factor of the first equation, right? So how do we solve different differential equations in this scenario? So, so here is how we would solve with special integrating factors, right? And really, it's about just looking at how we would uh, solve an exact differential equation like before, right? So, so if we have partial of m with respect to y minus the partial of n with respect to x is continuous and depends only on x, then we can reduce down the integrating factor like this. Likewise, if we have mu of n with respect to x minus the partial of m with respect to y equals to m, and it depends only on y, then you can use this integrating factor here, okay? And then the process for finding special integrating factors. So if we have a scenario where this equation is neither separable nor if it's linear, and if you compute these partials, if they equal, then the equation is exact. If it's not, we want to consider these two types